Hello everyone, welcome to the next lecture of electronic devices. Again, we are covering chapter number 2 on operational amplifiers. And this is our lecture number 4. So in the previous lecture, we discussed how we can use op-amps in closed loop configuration. And specifically, we are talking about an inverting configuration of an amplifier. So today we are going to discuss applications of inverting op-amp configurations. Right, so the first application is inverting configuration. We can use that as an inverter and scale changer, right? Since we know that V naught over Vi, which is a gain value, equals minus RF over RS. So this means that we can amplify the signal and we can invert the signal, right? Sorry. So this is the first application of the inverting op-amp configuration. We can invert the signal, 180-degree phase shift, and we can amplify the signal with a gain factor of G. Okay. So of course this was I guess already obvious. The second one is an interesting example, an application in which we can use that as an adder, a weighted summer. So which means that how we can use the inverting configurations to develop a circuit in which we are going to add a bunch of these signals together. We can use it as an adder. Right, so for example, look at the circuit that I'm going to draw, and then we will analyze that circuit. And that, oh sorry, I should probably do it. All right, negative, positive. V1, V2, Vn, R1, R2, Rn, I1, I2, In. 0 volts. And then we have a feedback resistor here, RF, and this is output voltage. All right. Now, if you look closely over here in the circuit, again, this is an inverting configuration of an amplifier. Our non-inverting terminal is grounded. We have a feedback resistor. But rather than having one input, we have a bunch of these inputs, right? We have a voltage V1, V2, and then we wanted to develop a generic equation, so we can go on to Vn. Similarly, all of these inputs are connected to a resistor, R1, R2 to Rn, and the current flowing through these resistors is I1, I2 to In. Right, so I already know that, and of course this is 0 volts. We are assuming this to be an ideal amplifier where our gain is infinite. Ideal amplifier. Right, okay. If I assume this to be an ideal amplifier, we're going to have a virtual ground and a 0 volts over here. So let's say IF is this current. All right, so I can easily see from here that my current I1 should be equals to V1 over R1. Similarly, my I2 should be equals to V2 over R2, and so on, right? So I can write a generic equation for all of these currents. Let's say, and then whatever the current that will flow over here, let's say this is current I, right? And so our current I should be equals to IF, because I positive equals I negative equals 0. We have a virtual ground, gain is infinite, so no current will be drawn into the terminals. So the current, so this summation current I will be the same as this current IF. So how can we write this current IF now? So IF will be equals to I1 plus I2 plus I3 to IN. In the summation form, we can also write this thing as, for example, A approaches 1 to N VA over RA. Right? Now, if you look at the summation equation, essentially this is the same thing. So what we are doing is we are summing up all these values, V1 over R1, V2 over R2, V3 over R3, and so on till Rn. So this is our value of the current. Now let's solve for this other branch, the feedback branch, where we have is our 0 volts equals IF RF plus V naught. So V naught becomes minus IF RF. We already know the value of IF. Put this value over here. So my value of V naught becomes minus RF into summation A1 to N VA over RA. So this is the value of the output voltage. And now as I can see from here, sorry, this should be equals to minus RF. Now as I can see from here, this is a weighted sum of all input signal, right? So output over here is, output is a weighted sum of all input signals. So what I will do is I will expand this equations, and then this thing will become more clear for you. So let me rewrite this equation. V naught equals minus RF and then the summation thing. So V naught equals minus RF into summation A equals 1 to N VA over RA. We can easily write this thing as right. So essentially what we are going to do is this summation will expand into minus RF into V1 over R1 plus V2 over R2 plus V3 over R3 to Vn over Rn. Right? Okay, so I can easily expand this as a negative into V1 RF over R1 plus V2, plus RF over R2, V3 RF over R3 plus Vn RF over Rn. All right. Now, if we look at this equation, so we can see that, right, our output is a weighted sum of all the input signals that we have applied at the inverting input, right? So these are all the input signals that we have applied, and what we are doing it at the output, it is a summation of all of these signals, and then we are inverting that with 180-degree phase shift. And right, so we have all of these voltage values here, and how we can get a desired gain of individual voltages. Over here, what we can do is we can also control the value of the gain for a specific input, right? So we can we can keep our feedback resistance the same, and then select the values of these R1, R2, R3, and all of these resistances to find the appropriate gain for these input values, right? So we can select different values of R1, R2, R3, Rn. We can select to get a particular gain factor for individual inputs by keeping same RF value, right? Since our circuit has just one RF, so we need to fix the value of the RF, and then we can just change the values of these R's, R1, R2, R3 resistances to get different gain values for the individual voltages. All right, so this is good. We ended up doing developing a circuit using inverting configuration to see a weighted sum. So the question is, sorry, what if you have signals with opposite signs? And you have to sum them. Weighted summation, right? As we can see over here from this equation, that what we are doing is we are summing up all the input signals. What if one of these inputs is a negative input, right? For example, a minus V2 or a minus V3, then this will be subtracted out. So what do we want over here is we have to redesign the circuit such that even for the negative inputs, what we are doing is we are summing up all of our signals. So let's do that example. And I'm going to drive that equation as well. All right. So let's look at this new circuit now. We have negative, positive. R1, V1, V2, this is RA, alright, this is V dash, this is V3, V4, RP, R3, R4, and then this goes all the way over here. And RC. Okay, so what we are doing over here in this circuit, interesting, is that we have two op-amps inverting in inverting configurations connected to each other. Right, so by now you can just, by the look of the circuit, you can understand what essentially we are doing is we are taking a weighted sum of V1 and V2, and at the output what is going to happen is it is going to invert it, and then use that inverted summation over here and feed it to the second summation network. So let's find out the value of the output voltage here in this case. Okay, so I'm gonna first solve for V dash, and then I'm gonna solve the next. All right. Solve for V dash. So if I will solve for V dash, I can see that this is a regular summation circuit that we did that in the past. All right. So V dash equals minus V1 RA over R1 plus V2 RA over R2. All right, now let's do the second part of it where we have V naught. It's also a summation circuit, so our V naught will be equals to minus V dash into RC over RB minus V3 into RC over R3 minus V4 into RC over R4. 2. So what we can do is we can replace V dash from 1 to 2. So our V naught will become equals to so minus V dash will be the negative of this. So we're gonna get V1 and we are gonna multiply this factor RC and RB with that. RB1 into RA over R1 into RC over RB plus V2 RA over R2 into RC over RB minus V3 RC over R3 minus V4 RC over R4. Right, so here's an equation where we are summing up the signals when we have some of the signals with the opposite signs as well. Okay, so what we will do now is I can quickly show you how we can use this in some of the example problems. For example, you have to design a weighted summer that provides output voltage of 2V1 plus V2 minus 4V3. Let's suppose you have to design this thing. V naught equals 2V1 plus V2 minus 4V3. So how you can design this summation circuit? Come back quickly, you can see it over here very easily. So the first one is 2V1, second one is 1V2, the third one is minus 4V3. Right, so you can see that I need a V1, I need a V2, and I need a V3 with a negative sign here, right? So using these values, RA over R1, RC over RB, I can design the circuit. Right, okay, since I need 2V1 plus V minus 2V3, is that it? 2V1 plus V2 minus 4V3, sorry, minus 4V3. So let's see how I can design this. All right, so this means that what I need is I need these resistance values. I need this combination of these resistances to be equals to 2. I need this combination of these resistances to be equal to 1, and I need this combination of these resistances to be equals to 4. All right, so I can for this, I have RA, RC, R1, RB should be equals to 2, RA, R2 into RC, RB should be equals to 1, and then 4 should be equals to RC over R3. RC over R3, okay, great. So from this, what I can do is I can do RC over RB equals 2 R1 over RA. 2 R1, sorry. So what do we have is, sorry, let me go back. RA over R1, RC over RB, RA over RC over RB. RA over R2, RC over RB. Okay, right. So I use this equation, RC over RB equals 2 times R1 over RA. So what I'm going to do is I'm going to put down this equation over here. So what I will get is RA over R2 into 2R1 over RA equals to 1. Right, so RA will be cancelled out with RA, and I will get a ratio of RA over R2 should be equals to 1 over 2.5 or R2 should be equals to 2 times R1. And the other thing that I got from this equation is my RC should be equals to 4 times R3. Okay, so RC should be equals to 4 times RC, and from here I found out that my R2 should be equals to 2 times R1. So these are the 4 resistances that I want. I want a resistance R1. I need to find out the resistance values of RB now. Alright, and in order to find out the resistance value of RB, so the way that to do is you can select any value, select for example a value of R3 and find R4, and then select R1 and find R2. Right, once you do that, put all of these values into one of these equations. For example, if you're going to put it over here, whereas you have two equations, one is you have RA, RC, your RC equals 4 times R3, RC. So you already know the value of RC. All right, so if you're going to put these value for RC here and R1 here, can we find out the value of RA? Okay, so we have all right, so I think we have two equations now. One, we have RA that we don't know the value. We know the value of RC is known, and then we have R1 is known, and we don't know the value of RB 2. And the second equation we have RA, R2 is known, into RC is known, and RB is not known. Okay, so what we want to do now is, once we find out the values of RC and R2, you can put down these values over here. So find RC and R2 from here and put down over here to find ratio RC, RA over RB ratio, right? And then you can use that ratio, RA over RB, RA over RB, right? I'm gonna call this as equation B. Find RA over RB ratio and then put that in equation B to find RA and RB values. So this can be easily find out, right? So essentially the idea over here is that, for example, if you were given an equation like this, what you want to do is you want to go back to this big equation and you need to make sure that these resistances values are going to define those gains. Over here the gain is 2, gain is 1, the gain is 4. So you can select those resistances values over here and then simplify these equations. Once you do that, we came up with these two equations initially. RC 4 times R3 and R2 equals 2 times R1. So the first thing is that just pick up any reasonable values of R3 and R1. For example, it could be 10 kilo ohms or 100 kilo ohms. Once you pick up these values, then use these values to find out the values of RC and R2. Now you have all 4 of these values calculated. You have an R3, R1, RC, and R2. If you will put these 4 values back in this equation, and this equation, you can easily find out the values of RA and RB. And this way you can select the values of these different resistances to develop a circuit where the value of the V0 is this. I will also assign you one of the homework problems of this weighted summer where you can see how, for example, how you can select these values, but the process is fairly simple. Then you can pick up initially some of the values, find the rest, and then use those values back in these equations to find out the remaining values. All right, so with that, I'm going to end this lecture, and in the next lecture, what we are going to do is we are going to do the remaining applications of the inverting configuration. Essentially, we have a couple of more applications that we want to talk about. One is how we can use an inverting configurations to develop these integrator and differentiator circuits. We can also take a differential or an integration of the input signal using this inverting configuration, and we will see how we can do that. We may end up using some passive elements, just as a hint. All right, so with that, thank you so much, and I will talk with you in the next lecture. Thank you. Have a good rest of the day. Bye-bye.